Hi, everyone, and welcome to this P4 Developer Days event. Today, Miroslav, a principal engineer at Altera, is going to present us a work related to P4 for AI and machine learning application. This session is going to be recorded and it will be available on the p4.org website together with the slide. And if you have a question, please feel free to do it, but you have to use the chat. So please write your question in the Zoom chat. And Miroslav, the floor is yours.
Okay, thank you very much. Thank you for introduction. And I want to talk about today about some maybe not how to say not trivial application for the P4, yes, which is the connecting P4 and the AI/ML. Why we need to connect we want to connect the P4 with the AI/ML. Yes, the first of all the technologies, AI/ML technologies, what we know, for example, from the LLMs or the are very slow, and the packets rate, what we need to processing are very, very fast. Yes, we are going to send of the hardening of the millions of packets per second. In some use cases, and I believe that the firewall use case, for example, the handling of the packets, yes, in the way how the machine learning can do here, it would be the very useful. Let me talk about for example, some use case. Yes, what we are talking. Yes, for example, on the screen you can see, for example, the screen with real firewall from the firewall vendor F5 networks, and what you can see here, it using this screen is generated, yes, of the on base of the some new techniques, yes, in the firewalls called the volumetric firewalling. And what it means, the volumetric firewalling, yes, we have when we implementing the volumetric firewall, we defining of the some rules on base of the traffic amount, yes, and of course the traffic type, but also the traffic amount. The traffic amount, what is sent, for example, the packet rates or the some trials to make of the some operation is to, for example, could be a suspicion to the firewall, and it could be considered as an attack. Yes, for example, imagine the situation that you are making the logging operation or the starting of the, for example, just the TCP sessions. Yes, here, and you know, for example, that in normal operation, the given user is the providing, or the users, yes, from the specific area that they are providing or the generating, for example, 10 SYN or the trying to establishing the 10 sessions per second. Yes, here it is the normal operation. But some way, for example, you can see, okay, that you see something different. These guys, what you are filtering here, are trying to connect for example, thousands times faster. Yes, here it should be it could be normally for example, the packets of the operation are the correct. Yes, here, and they are allowed here. What is the suspicion? The rate of the packets is very suspicious. Yes, and here you can see on the picture on the left side two possible cases. Yes, the one is to, for example, some medium weekly traffic. Yes, here, which is the much higher down, that is then higher than normal, what you observe here. And at the end, you see the small red dot, which means that you are generating, someone is generating the traffic, the 10 times faster than suspicious traffic in the middle of the screen. Yes, here, and also it is also from the, for example, single IP address. Yes, which means that it is for sure some kind of the attack. Yes, here, which could be determined only by the, for example, some processing of the packets which are the correct, are allowed here in the network, but we should set our filters in the firewall to the using the using just, for example, and to achieve such results. Yes, and so such detecting of the such attackers, we are using very often the ML techniques are using. Yes, let's go back to the first screen. Yes, how we can use the AI. Yes, unfortunately the packets are arriving are the very bad input for the AI. Why? Because the good thing in the packets is to data are the structured. Yes, we have the headers. Yes, we have the values in the headers. And but inside of these headers are filled with some value which normally are random. Yes, here, or depending, for example, at the geolocation of the sender. Yes, or at least for example, we have the some sequence numbers. Yes, which should be the, for example, randomized by the definition. Yes, and using the normal, for example, deep learning techniques. Yes, which are the people are using with the, for example, in the LLMs, is very not use very difficult here due to number of the combination. Yes, and available and also it means the models. Yes, what will be generated by the just to using deep learning techniques. Yes, used for the image recognition or for the text recognition. Yes, here what be the creating the very big models. Yes, here, and from the perspective of the performance of the model, the bigger model means the lower performance. Yes, and we are interested into the some some process of the how we can handling the traffic and provide to the AI model the more squeeze data to make sure that the model will be, for example, much smaller, and thanks to this one faster. Yes, and also we are in the Altera, and we are making the FPGAs application. And very important to us is to maybe we can even feed the, for example, the processing of the packets. Yes, and the AI inference engine inside of the single chip. Yes, to achieve some incredible speed. Yes, here the process of the squeezing model. Yes, of the limiting of the complexity of the model is called normally the quantization here. And additional problem with the AI and the complexity of the traffic is to packets normally are delivered in some sequence. Yes, and for example, in the and very important here is to getting the, for example, some kind of the to determine the what is the problem with the traffic. You should know the sequence. Yes, and handling of the sequences of the packets also is to very difficult to handling, and normally by the AI, and normally it requires the some kind of the even the for example models including the transformers or the some models which are called recursive neural network. Yes, here. And for example, if the using of the some modifying of the traffic or some modification of the transforming of the data, yes, what we're receiving, yes, as the part of the packets into the some information which is the more better the AI model can better consume, that it is the additional advantage what the P4 can provide here. That I was talking, and here we can go back to the, for example, the to our picture, yes, and the real use case of the volumetric AI, yes. In this example, what we are talking here about the. You can imagine that for example, how the model can looks like. Yes, I'm talking here about normally the firewall are the maybe not looking into the, for example, some kind of the let me say that the content of the packet. They are the more precise here, and they are, for example, detecting of the more sequences. But for example, you can imagine that for example, some firewall models could be very useful in the case when you're providing for example, the different information. Yes, and here we can use for example, the P4. Yes, here what information can we determine from the P4? Yes, that from the P4 as the packet, even in the simplest and the standard P4 architectures. Yes, like the V1 switch, we have the information like, and we can get the information of determine the packet, for example, the packet size. Yes, we have the timestamp. Yes, with the timestamps, we can determine for example, interframe packet gap. We can make when we have for example, interframe packet gap. Yes, here we can determine if we have the burst traffic or the not burst traffic. Yes, here we can determine if this traffic is the L2, for example, L3, L4. Yes, normally the most of the traffic is then encrypted, and probably using just the standard P4 processing as the packet, we will see nothing more better. But we can also determine the session, and this information could be the good input to the inference engine, what we are connecting to for example, to the P4 pipeline, like as the P4 extern. Yes, here. And thanks to this approach, we can, for example, make the interesting implementations, yes, of the firewall. For example, imagine that you are interested because from the firewall vendor statistics, yes, most of the attacks to your infrastructure is going from some specific geos. Yes, here which are mostly attacking this one. Yes, inside of the P4, you can, for example, limit when you have using the ternary search. Yes, in the P4, you can limit for example, on base of the determining of the ternary search or the LPM or some kind of implementing of using P4, some kind of the LCL using the ternary table. You can determine, okay, I am interested only with the traffic from the specific networks here. And it is also the connecting of the traffic. It is limiting of the traffic only to for example, the attackers from the specific geolocation. Yes. Additional use cases to detecting of the flooding attacks, yes, which are very simple to do, and the P4 with the timestamps, for example, and the arithmetic operation on the timestamps in the information of what we have, we can determine, for example, the burst of the packet. Yes, if for example, some level of the rate rate of the sum of the packet types, yes, like the, for example, SYN packets, yes, or the, I don't know, the just bare IP packets, yes, or the some additional attacks, yes, is increasing, yes, here, and moving and crossing the, for example, some boundaries, what we determined as the, for example, as the attack, yes, here versus the normal traffic. We can connecting this few features together, yes, like the, for example, whitelisting and the flood generation, yes, here that we can create some new interesting capabilities just using the P4, yes, here the model. That additional interesting, for example, the application, yes, what we considering is also, for example, detecting of the some kind of the vishing. Yes, vishing is the special attack to the operator, to the users. Yes, here where, for example, the attacker is generating the voice and trying to convince you to make of this some kind of the operation. Yes. And what we know about the, for example, how different is the voice traffic, yes, in the mobile operator, yes, for example, of the data center operator versus the, for example, normal data center traffic like the, for example, Netflix or the Facebook, yes, and whatever, yes. The difference is the, for example, the voice packets will arrive in the without the burst. Yes, every packet will be arrived into the, for example, more or less same, more or less same period, yes, because it is voice, yes, in the voice packet, and the packet are the generally shortened. They never appear in as the burst, yes, here. Opposite to the, for example, the Netflix or the Facebook, yes, when we have the data, when the burstiness of the traffic is just to nature of this traffic, yes, the senders of the traffic will be always send this as the burst because it is more efficient from the server generating this traffic, yes, here. And this, for example, determining of the vishing, yes, or the, for example, the voice session, yes, here, using just to AI ML, yes, like this one, yes, here is to only possible by the making of the some AI ML techniques, yes, here. It has the some application of the really the some attack which could be detected only with the AI ML techniques, yes. Or, for example, in the different way, you can imagine, for example, you're making of the some kind of the heuristics, yes, here, which is the very difficult to implement even in the software, yes, where you have the performance problem, yes, or and even more difficult inside of the hardware, yes, here. So, for example, in our models, yes, what we are achieving, yes, here, when we are connecting the model inside of the FPGA, we are able to achieve, for example, even depending of the model, what we are using, the 11 million packets per second. Yes, it is the 11 million packets per second is to really the using of the simple model. We call this model MLP. It is called the multi-level perceptors here, which is generated by the is part of our FPGA logic, and it is just works as the extern to the P4 code. Yes, here, and at the end we measuring the performance, yes, of the system by the for example, we have the packet, yes, and in the response packet we providing the response of this one. Yes, it means that for example we can determine the 11 times per second if the for example the session is for example the voice session versus for example the data session. Yes, if this is voice session, we can, for example, using our P4 architecture, move this out to the to the, for example, different location of the adding of the some, I don't know, legal intercept header, yes, and we can just to check the if the specific voice message is here could be vishing or not vishing. The currently probably the determining if the voice message or the packets related to the voice message is maybe too big for the today's FPGA, but what we are doing, we detecting the voice from the data packets, yes, for example, yes, here. And how looks like our the P4 architecture? Yes, we are using the FPGA here and the P4 inside of the FPGA as the feature extractor. And in our example, what we normally showing and the presenting to the to customers and the people who are interested here, we're presenting. Okay, here is the we sending of the SYN packets here, and we detecting that the rate of the SYN packets is the exceeding. Yes, here we detecting using the some very simple model. For example, the number of the SYN packets increased. Yes, here, and we detecting okay, this is some alarm to the firewall or not. Yes, this is of course very simple, and you can say that the for example, you can do this by simple if, yes, in the code, yes, in the even inside of the P4 code, yes, to do this one. But it is very simple, and the application is here, which shows the how you can use to implement the own models, yes, or the own application on base of the packet, yes, using just to P4, yes, which is transforming the packet fields here into the data which could be analyzed by the AI ML engine, yes, here. Let me talk a bit about the how looks like the generally the process of the preparing of the AI ML model with P4. Yes. The first of all, what are the trained data? Because in many applications that and the biggest problem, generally the biggest problem for the any kind of the AI ML is to how we can find the trained data. For data for the training, yes, the algorithms are the very well known. They are the simply simple. Everyone thinks that they understand what they are doing, but the real problem for real application is to training data. Yes, how we can train this data and how we make the label them. Yes, in our demos, what we are doing, we are getting the pickups. Here, the pickups with the timestamps, where and we creating the P4 code model using the Python. And inside of the Python, we just to making of the P4 processing, P4-like processing, and inside of the P4, we detecting or we getting or the reading of the or creating of the features, yes, and in the same way how the P4 code will be used, will be generate this one inside of the real hardware, yes, here. And when we have these features of this transformation of the pickup or the header fields, packet header fields, yes, into the, for example, the ML to the data, which is the made by the ML classifier, we are using the, for example, in our model, we are using the Keras, the Google Keras classifier, and we making the just to training inside of the software or using the GPU that it has, and on base of the labels, yes, here we are processing the, for example, we making the processing and the labeling and make the training process of the system, yes, here. And next, what we are doing, that it is very important that thing that we are training, evaluate, tune, train, evaluate, tune, train, evaluate, tune for optimal model performance. Yes, here it is the same, and it is still doing. We are using the software tools. Yes, using the CPU and using just well-known the models. Yes, here. When we have the model in the software, which provides us the sufficient results here, what we are doing, we downloading this model to the or the making the transforming of the model into the FPGA, yes, and we connecting it together with the real P4 code generated by our P4 compiler, or the which is called the P4 suite for the FPGA. Yes. For example, in this example, classify model classifier, we are using the six domains of the data. Yes. For example, the 6 is the very small, but as I say, we are interested into achieving the highest performance. Yes, here for your comparison and the curiosity. For example, the LLM models, yes, for example, ChatGPT is using the billions of the domains of the parameters, yes. Then in our model, we're just using inside of the FPGA, we are using 6, yes, here. And we're making the training on base of this one, this features. Yes, we are using the 6 feature domains. Yes, here which could be, and thanks to P4, of course, if we want to use for example, deep learning, yes, here, or the method which is used for the learning of the LLMs, probably we should extend this number of the features by the hundreds times or maybe 1,000 times more to achieve the same result like we are doing with the P4, which is transforming the packets, yes, into the, for example, features readable by this ML classifier. Okay, what tools we are using for the AI ML generation for the FPGA? If you are interested in the FPGA, we can use for example, the Altera AI suite for the FPGA to create the AI model, and we can use the Altera's P4 suite for FPGA for generating the feature extractor. Yes, also what we are using in our demo, we are also using the HLS for ML. It's tools which is created by the CERN people, yes, maintained by the same people, which also supports our FPGA. And also the last possibility, what we are considering is to creation the model using the MATLAB deep learning toolbox, yes, which is the tool where provides the very efficient model, because inside of the FPGA we can use the tons of the available DSPs to make the operation to make the operation and the numbers, yes, because really what the AI/ML model is doing, it is just to making the operation like the multiplication of the matrices that it is where using the DSP, yes, and the code provided by the MATLAB is very efficient, yes, here. Let me show what P4 features are extremely useful, and what we are using for our test. Yes, here. The first of all, we are using the counters. Yes, because in the volumetric firewall, all the name like the volumetric firewall is call is just to getting the volume of the traffic. It means that we should count the traffic. Yes, and here the P4 features related to the counters. Yes, are really extremely useful to us to such application. Yes, and we can use with the PGA. Really, we can use the two models. Yes, with the counters. Yes, one is to generating the internal counters as the P4 language, or for example, you need to having for example, millions of counters. Yes, here you can use we have also the externs. We can access these counters as the extern connected to the control by the P4 code. Yes, here. Second very important thing, extremely important to us, is to using of the registers concept. Yes, why the registers are important. Yes, without the registers, we can keep of the some state of the connection. What is the state of the connection in our model? Let's talk about the P4 float rate estimator. Yes, what is the rate? Yes, rate is the packets per second. Yes, we don't have the counters. Yes, of the, for example, rate evaluators. Yes, in the P4. Yes, there is no such concept. Yes, but what we have is the timestamp, and we have the register. Yes, and we have the when we have the timestamp, for example, in the nanoseconds. Yes, or the microseconds. Yes, whatever what speed we are using. Yes, we can store this value in the register and wait for the next packet of the same type which we are interested. Yes, if for example, we know with detecting this traffic, we can, for example, determine, or for example, the time between the packet arrival, or for example, we can determine okay, for example, the some level of the packets that some information like, okay, some time appeared, and during this time we for example, receive some number of the packets. Yes, if we know for example, time between events. Yes, and we know how many events happens between this events. Yes, we simply can determine the rate of this event. Yes, here it is also the very nice capability of the P4. Yes, here where we are using of some part of the timestamp to determine what is really to determine or the providing of some kind of the time sense. Yes, to the generally stateless the P4 pipeline. Yes, here what we implemented inside of the hardware. Yes. And second thing, which is extremely important here, it is we are using the extents. Yes, the extents interface. Yes, and the definition of the extents. Yes, in the P4 code. And the language, the P4 language, provides the capability to define any kind of for example, the inputs. Yes, any kind of the outputs. Yes, here. So we can make the very nice interface. Yes, from the P4 code to the AI ML engine by the using of using the extern interface. Yes, it is for example, when we have the 6 features. Yes, here, or the 6 domains of the features that we just using of the defining of the 6 inputs. Yes, are to the extern. Yes, here, and we expecting from the 6 inputs for example, the information from some output. Yes, what we can process next as which could be the part of for example, output packet. Yes, which response, or we can ignore the value. Yes, here it is really important to us, and really nice features. Yes, how we connecting. Yes, and of course the arithmetic and the logical operation. Yes, that's as I explained. For example, we need to make of some arithmetics. Yes, to make sure that determining the rate of the packets. Yes, here because the determining rate is the ratio something to something. Yes, here that it is really the that it is reason why we are using the P4. Because with the P4, really you can imagine that you can build FPGA or that you can make the packet processing machine learning even without any knowledge about the, for example, the FPGAs. Yes, you can make the system, yes, which they're running, for example, 11 times per second, making the inferences 11 times per second using the packets, yes, here, and you don't need to know the RTL to do this, yes, here, which is the extremely useful target, yes, for the customers, yes, who wants to try or the creating the more complex or the proving the very concept, yes, here, or the very ideas, yes, regarding the ML in the packets, yes, here. Unfortunately, the one problem, yes, with the AI ML for the networking is the lack of the data sets, yes, here. In our examples, yes, what we were doing, yes, here, we were using the pickups, yes, here, and really the generating of the, for example, the pickups from the making the synflat or versus synflat, yes, we just use the hackers tool like the A-Ping3 HPing, yes, here to generate this one. Yes, that it is really the something what the people should work a bit. Yes, with the images. Yes, for the some data set standard data sets from the image recognition. Yes, of the text recognition. That it is not a big problem. Yes, to provide. Yes, here, but from the packets, it's still the some many things to do here to make standardize and for example comparing this solution, yes, to the something which was created by the others, yes, here that but to me it looks the very interesting use case, yes, not very trivial, yes, because the P4 was created just to having the switches of the routers, yes, here, and here we're trying to build firewalls and building the even the firewalls which are the extremely difficult to make using the pure software. Yes, here with this approach that it is why I like this use cases here, yes, to show the for example the power of the P4 languages here and really the some future vision, yes, what the authors of the P4 just had inside, yes, it is, and this really demos and this AI/ML just proves that the language designed 10 years ago for the networking is still working and it is still valid. We are looking to the more and more new use cases here, like here. Yes, thank you.
Thank you, Miroslav, for the presentation. Do you have some question from the audience?
No, none from me. Thank you.
So Miroslav, what are other AI use case that where you can use P4 in order to where you can use P4 implementation that can help to design a new networking designs?
Yeah, that it is very good question. Yes, for example, let me start from some tricky point. Yes, here what we are thinking, what we believe is to, for example, some problem of the congestion control. Yes, in for example, the initial paper, yes, from the group made from when the P4 was defined. Yes, from the Stanford guys and. that they mentioned that the P4 is to, for example, do not include the things like to congestion control. Yes, but what we are thinking, yes, and really the one of my doctorate's candidate, yes, here what I'm driving here is had the idea about, for example, maybe we can implement, for example, make the implementation of the I don't know, the stateful protocol, yes, like the Rocky, yes, here in the AI, or the Falcon, Google Falcon, yes, here, which is the much better to implement using the P4, using just the P4, and maybe using the extern, yes, here we can connect, for example, the AI ML engine, yes, here, who will be implement some congestion control heuristics on base of the inputs provided by P4 code. Yes, here. For example, you can see the P4 code is implementing of the protocol, yes, the retransmission and so on, but also generate the signals, yes, to the AI ML engine, yes, which is working as the generating the congestion signal. Is the congestion or not congestion? Yes, in the situation what we are here, and is the congestion or not congestion? Yes, today, for example, implementing, if you know, I spent many years in the under congestion control and the TCP, yes, in my previous year, and you can't imagine how the big heuristics it is. Yes, here it is some incredible that the people invented hundreds, if not thousands, yes, congestion control protocols. Yes, here, and of course from their perspective, every of them has the big sense. Yes, here, and to me, for example, is the problem, okay, how to implement this in hardware, yes, in the kernel. You can do this simply. You can do this simply, for example, by the changing of the model, yes, changing of the heuristics, yes. In the hardware, wow, it is not so simple, yes. Here, you must to changing the heuristic, you need to recompile, or maybe you need to provide the AI ML model which will behave like this heuristics. Yes, it is very promising, but currently the P4 community really I don't see the first thing to achieve this model. We should implement the termination stack. Yes, for example the TCP Rocky. Yes, here, of course, which is doable using the P4. Yes, here with all the methods. Yes, we have the registers. Yes, we have state. Yes, here it was just to work how we redefined and how we need to do what we need to do here to providing the same information to making sure that we can train this model. Yes, here and really it is to me it is the very interesting feature. Yes, which the community, for example, it is maybe work to talk more with the community. Yes, here, and some examples is here it is the big area for the research, especially in the AI data centers. Yes, here all the NICs what you are using must be hardware. Yes, here and if this is the hardware, why not generate them in the P4? Yes, make it scalable. Yes, here it is really my vision and something that I work with this student. Yes, here to make sure that what can we do this here.
Okay, very interesting. Please feel free to join our working group if you want about P4 language, for example. If you have some proposal, you can present something there if you want. I don't know. There are any questions?
Yeah, hi. Can you hear me? This is Ram.
Hello.
Hi, Mirak. Mirak, can you hear me?
Yes, we can hear you.
Okay, Mirak, good presentation. So one question I have is you have these machine learning models. So are you running this machine learning model on the FPGA fabric itself, or are you on the HPS? Where
No,
exactly?
in FPGA. We are generating this to the using one of these tools. Yes, here. Generally, we currently have the integration. We have the architecture, yes, P4 architecture. We've connected the AI ML engine, which is generated by generally today we're supporting HLS for ML, but also we can do this using the Altera I suite for the FPGA, and we are working on with the MATLAB to make sure that it could be also generated, but it is inside of the FPGA.
Okay, so you're not running any model on either the host,
No.
CPU
No.
or on the HBS.
No.
Okay, okay. But these models could be fairly big. In fact, as you know, we are going through some of this. And how are you able to fit in those, especially large models into the FPGA?
Let me say we are not fitting because they do not fit. Yes, our model, what we are trying is to just to MLP, yes, with the 3 layers and which is not very big. Yes, here that it is still the work in progress. Yes, here that it also depends on the data. Yes, for example, we are going into use this MATLAB deep learning because it provides the much better FPGA code. Yes, here which much more efficient than, for example, just HLS for ML, but still it is I would say terra incognita, as the unknown that land. Yes, here where we will finish. Yes, here it is still I'm talking here about our research projects. Yes, what we are working. Yes.
Right. Right. Yeah. So one more question. So obviously you need to, create the P4 pipeline. So is it still made independent of the model, or are you able to generate the pipeline architecture based on the, ML model?
It is really what we are doing. We defining the ML model as to 6 features, yes, here, which are defined as the external interface to P4, yes, here.
Okay, but the P4 is independent, basically.
Yes. We really have we're building the image, yes, for the FPGA. Yes, we have the 2 separate tools, yes, here, and as the end step, yes, we're connecting them together, yes, here to create one working image, yes, inside of the FPGA, yes, here.
All right. Okay. Thank you.
Any other question? So I have a question about the uh, mm, architecture of your FPGA. So I would like to know if is it possible if you use as a architecture like you base your architecture on portable switch architecture, or you have something a bit different?
Generally, in Altera, yes, in our P4 compiler, we use the concept of something generic use case architecture, yes, because of the flexibility of the FPGA, what we can do, yes, here. And for example, the big difference is between our P4 compiler, yes, and for example, the community compiler like for V1 switch is a part of the P4 file, yes, what we're delivering. Normally, it is the only input, yes, what you're creating for the PSA or for V1 switch, yes, here, or for the simple switch simulation, yes, it is P4 code, because the details of the architecture are inside of the, let me say, compiler, yes, only compiler knows, yes. In our approach, we have 2 files, yes. One file is to P4 code, and the second file is the architecture file, yes, here. And really, it provides us the very big flexibility as to create of the generate any kind of the, maybe not any kind, yes, here that it is far from the I can imagine, yes, here, but really we can be the much more flexible, yes, here than tools which are the available as the open source, yes, here it is.
Okay, thank you.
I didn't quite catch the FPGA that you're running on. It was an Agilex I series?
Really, the demo, we can run this on any kind of the FPGA, but really the specific demo was made using the Stratix 10. Yes, here.
Oh, the
it was,
Stratix 10.
yeah,
Interesting.
yeah, it was really it was the, but really the code what we generate is really the not FPGA specific. Yes, we generate just to RTL, which can fit into any Altera FPGA. Yes, here from Agilex 5, yes, Stratix. Yes.
Yeah, we use the Xilinx FPGAs using the ESNet SmartNIC stack, and it supports P4 runtime in the FPGA. And we just received two Agilex 7 M series FPGAs with the 400 gigabit a second ports. We're very interested in doing P4 on those. And so I might reach out to you to figure out what you're up to.
Yeah, please send me an email. Yes, you can access me through the LinkedIn. Yes, or that it is, or that.
Thank you.
Yeah, we are happy to cooperate here. Yes, that it is.
Other question? Okay. So I think that we can close here. Before to close, few two information. So I don't know if you are aware of that the P4 workshop will be in OCP Global Summit in October, and we open the call for paper. So if you want to apply, please check the P4 website to get more details about the P4 workshop. And the deadline for the paper is the 1st of August. And a second announcement is that the next P4 Developer Days, made also by Altera, will be the 6th of August. And the use case is a gateway use case architecture for network application. And so thank you so much, Miroslav, for your time and for your presentation. And thank you all for to join the P4 Developer Days event, and have a nice day. Bye.